the gas problem and how to get rid of it. So, a little background. NGC 1275 is the brightest cluster galaxy in the Perseus cluster, which is an understudied, very massive cluster. It's just as massive as Coma, but it's in the wrong part of the sky, so people back in the good old days of optical work didn't get telescope time. This is my slide from what I would have guessed Andy would have said, to point out that if you look at the center of Perseus, this is the center of the cluster right here from a Chandra image, and you do high-pass filtering, you see these bubbles, these low regions, you see complex structures, and you see ripples. It's not a simple medium, simple isotropic homogeneous medium. The cluster has a dispersion of 1,000 kilometers a second. The mass of the cluster is probably on the order of 5 to 6 times 10 to the 14 solar masses. The gas mass is 1/7 of that. And as the brightest and relatively nearby cluster galaxy, 1275 is a fantastic place to understand how galaxies interact and where their interstellar medium comes from with respect to a galaxy cluster. Okay, so here's a close-up of the central part from Chandra, and what you can see is you see dark absorption from something called the high velocity system, which is in the foreground. You see a bright nucleus. 1275 is actually a mistaken galaxy for low redshift. It has a Seifert-1 optical spectrum and a double lobe radio source in it. Here's the non-thermal radio, which this is the core of the high brightness, which fills these two bubbles. This is a likely fossil radio bubble, and there are other possible bubbles out there. Notice that the initial outflow in a standard FR2 or FR1 radio source, of course, is bipolar, while the inflow will tend to happen over 4 pi steradians. So you have to be careful about how the feedback works. It's not going to be directly just the gas pushing things out. You've got to also allow some way to isotropize the energy from these outflows. Clearly, if this is a rising bubble, the jet in 1275 then must have recessed over time, and that may be part of the process that's going on. The PV work, in this case, is about 3 times 10 to the 59 ergs for these inner lobes as they stand right now. So there's a large energy content. The high velocity system I'm not going to talk about much, but you ought to be aware of it. This is the infalling galaxy, right here, what's left of it. What you're seeing is you're seeing it projected. The center of the galaxy is about here. Behind it is Perseus A. These streamers are dense molecular clouds making stars out of it. The galaxy is moving at 3,000 kilometers a second with respect to Perseus, and it's redshifted and in front of it, so therefore it's an infall velocity. There was a very nice study done by Gilman et al. That showed the distance is something like 60 kiloparsecs based on the X-ray absorption against these regions, which are molecular. That's how we know this is molecular gas, to answer the questions from yesterday about stripped molecular gas. And again, the kinetic energy of this is on the order of 10 to the 59 ergs. So you have to remember that these brightest central cluster galaxies also can be influenced by infalling material coming into the cluster. A famous feature... Yes?
Here's the center of the galaxy?
The center of the infalling galaxy is right down in here.
Because you've seen other images where that's clear? Or?
Actually, Vera Rubin measured a rotation curve in the center parts.
And it's 60 kiloparsecs from the BCG.
Right. BCG is here, 60 kiloparsecs out is this thing. Velocity redshift 3,000 that way. 3,000, yes. It's puffed rice. It probably came. I think it probably came out of a void. It's a pretty high peculiar velocity. Let's put it that way. The other feature of NGC 1275 that was discovered actually by back in the 1950s is the huge system of ionized gas filament. Here's an H-alpha image from Chris Consolise's thesis at Wisconsin. And here, this is 90 kiloparsecs. Here's an example of one of these wrapped structures. So a few things to notice about the filaments very quickly. The outer edge is fairly well defined down here, and notice that in this region the filaments generally either end or are tangential. You don't see filaments concave in, which suggests that it's an outflow producing these structures. The northern extension here suggests something to do with a past jet or past feature of some kind that went up there. The filaments look very dynamic, and they're very large scale. It's hard to get used to the scale of this, so I apologize for doing an astronomy 100 trick, but here you go. Here's M31 to scale. So the filament structures are the size of galaxies. So they're really large, okay? So we're going to talk about now the ISM in this galaxy and try to put it into the context of the talks that were yesterday. So a little bit of physical background. The temperature drops a little bit in the center to about 3 keV. The density stays relatively flat. The pressure remains a few times 10 to the 6th and drops rapidly near the outer part of the galaxy. So you can work out a few things about the situation, assuming equilibrium. First of all, I'll come back to that. There's about 10 to the 10th solar masses of hot medium inside of this 25 kiloparsec radius, which is approximately where most of the filaments are as well. So this zone here is also the primary filament zone. Other than the northern extension, they fade out right around in this area. Okay? The ionized gas density would then be about, from the pressure, about 100 on the average for pressure equilibrium. Any molecular gas, 10,000. Equilibrium magnetic field, 100 microgauss. And if you were going to support the filaments with a thread, you would get something like 12 microgauss if they were only ionized gas, but they're not. They're molecular, so there's the problem. How does the balance look like in this system? I like this diagram because the lighter books are heavier than the heavier books, and that's pretty much this galaxy. It doesn't work. The cool gas sinks are the AGN, and potentially supernova driving things out. That's the way it's a sink. Gas heating, so these are sinks out of the galaxy. Star formation, high velocity impact. If the gas comes in, if that high velocity galaxy hits with a diffuse medium instead of just bullets of dense gas, then the shock heating will be substantial and will increase the temperature and therefore expand the gas. Cool gas sources. The dominant one, of course, is the intercluster medium. There's also stellar mass loss, and there's a stripped gas from galaxies falling in. So how does it all work? Stay tuned. So here's an HST image that Andy Fabian and his team put together by being very clever about how you use HST. And the point is the filaments, when you see them, are first of all very long and often very thin, like this. And very long, I mean scales of order 10 kiloparsecs. So filament widths of less than a kiloparsec, lengths more than 10 kiloparsecs.
Can you put this in perspective, the size? Where were these cavities?
Where were the cavities? The big cavities up here. These rays I'm going to come back to. The bubble sits up, the horseshoe sits up here, and the bubble is the next floor up, looking at the surrounding nuclear power plants. Okay. So what you see here is you see this complex system of ionized filaments. You see some sites of star formation, but they're very few. And you see that the filaments actually have a relatively uniform structure, and that their brightness does not depend immediately on radius. It's more, well, you have multiple ones stacked up. So you can do an optical analysis, a Dumbo analysis, where you work out the emission measure, the width, and you get a mean density of order 10, which is 10 to the 5th if they were at a density of around 10 to the 4th degrees for the temperature. So the mass in H2 is only the order of a few times 10 to the 8th solar masses. So it's a few percent in ionized gas of the total mass of the intercluster medium in this region. The fact that the filaments are thin and extended strongly suggests magnetic stabilization. They don't seem to be part of anything else. There's nothing else around them. It's not as if they're filling in. And you often see these very, very long, thin structures. So the model that we've put together, largely working with Ellen Zweibel and Madison, and also the group in Cambridge, is that these are basically magnetically defined, at least, structures in the interstellar medium. So this is a very complex medium. Now, it looks very explosive, but it's not. Here's a little bit of IFU data, and notice the range and velocity is basically the internal velocity of the galaxy. And the velocity range, and also Nina Hatch did this for her thesis, Vera Rubin before that, are a few hundred kilometers a second. So in terms of the hot gas, these are strongly subsonic. They're moving at velocities that are characteristic of the variable velocities within the galaxy. Dispersions a few hundred kilometers a second. And within the filaments, I won't show you that slide because of time, the filament structures themselves are very coherent in velocity as well, with very small velocity ranges, which again suggests they really are coherent structures consistent with the magnetic idea. So the filaments, much less than the sound speed, it's dynamically cool. They're not remnants of high velocity shocks going out. You actually have a hard time anyway. This is a hot medium. If you shock it, it gets hotter, and then you have a cooling time problem. It's a race as to which happens. The energy in the filament is on the order of 10 to the 57 or 10 to the 58 ergs. So not gigantic. Now, this was all fine. This is the classical view of the filaments. And then along came work, beginning with work with IRAM by Salome et al. Actually, Christine Wilson before that with JCMT. And then a lot of follow-on studies showed that there's a strong molecular component to these as well. Here's the WIN image from Consoli's thesis. Here's an image of the H2 S0 line, infrared line. They're identical. Here's this. Here's the horseshoe. Here's the horseshoe. Here are the northern filaments. The filaments contain molecular gas. And if you take a solar CO X factor, the mass is several times 10 to the 10th. I don't think you know that well, but it's probably not off by a factor of 10. The estimated mass then in the filament system, it's mainly molecular, and it's got a mass of 10 to the 10th solar masses, which is on the order of the ICM mass within the galaxy. So these filaments are not a minor factor. These filaments seem to have absorbed, if you like, the equivalent of the gas that's inside of the galaxy. And they're mainly in terms of mass molecular. They have a high internal turbulent velocity. By the way, this is a synthesis map by Lim et al. There have been a lot of studies trying to understand the molecular content of the filaments. But of course, the small ones are too small, and this is too far north for ALMA, so it's hard to do. So the picture that we come up with is that the filament consists of an ionized skin, inside of which are molecular clouds. Given the pressure and the low velocities, near pressure equilibrium implies, of course, mean density of 100, which gives you the filling factor. And then also, you have ionized surfaces. The molecular gas is at about 10 to the 4th per cubic centimeter. But along most filaments, there's no evidence of star formation. There's some star formation, but most filaments do not make stars. So star formation, while it's a sink, most filaments simply are filaments. And the answer to this may lie in the very large velocity dispersions that are observed both in the ionized gas and in the molecular hydrogen line of something like 30 kilometers a second. So a lot of energy is also going into turbulence. So it's a multi-phase medium, which is a key to this particular feedback process.
Sorry, Jay.
Yeah.
So you assert that there's no star formation.
I said there's only limited
little
star
star formation.
Yes.
So how can you tell?
HST images are very sensitive to OB stars, and we even have UV images in some of them. We also can tell the spectra of these are different from the H2 regions. When we find regions with star formation, it stands out like a sore thumb in terms of the emission line spectrum.
Okay, so both emission line diagnostics resolve star formations and UV.
And UV. But of course, you can always hide some. You can always hide some star formation. You can always underestimate how much there is. There's still a significant star formation rate, but most filaments are not star forming.
Thank you.
Okay. So what's going on with the filaments? We had a thesis in Madison by Jen Stone, which follows on the work that Becky was talking about yesterday, where you look at the stability of a magnetized medium in different pressures. And generally, in a high pressure region, you expect that a cool magnetized region with partial conduction will actually stimulate condensation rather than evaporation. But that's a tricky calculation. All that you know for sure is here's the H alpha image from Consoli's, here's the X-ray image of the same region from Chandra, and you can see that the filaments stand out in soft X-rays, 0.51 keV, and are gone in hard X-rays. So it looks like certainly the filaments are affecting their surrounding. They're either evaporating into it and cooling the medium, or I suspect more likely in the inner part of the galaxy, actually condensing. So it may well be that the filament structures still stimulate filament growth, as Mark Boyd and company had really argued some time ago. So this is the filament seeding issue. Why is it an issue? To get cold gas out of a hot medium, you have to do more than just compress it. If you adiabatically compress it, it just gets hotter and you go nowhere in terms of cooling time, and it will re-expand. It's overpressure. So what you have to do is you have to collect and cool the gas by a large factor. Temperature in there is over 10 billion degrees. And this is hard to do. Okay, so how could you make filaments? We don't have a complete model, or at least I don't. But there's a very good idea that was put forward, which is the rising bubbles that we've heard about. Here's the large X-ray bubble. The contours are the H-alpha filaments. Here is a model of a flow diagram. And there's a feeling that the material is being pulled up as this bubble rose and is ending up in filaments. This could happen in the sense that we're seeing here a wet phase of a bright cluster galaxy with material being moved outward. Moving outward, the pressure drops. It's more likely that the filaments will evaporate or do something else. So let's look a little bit more closely at this region and see what the structures are. Here's the horseshoe right here, which if you have better data than looking up here, you can see it consists of many tiny filaments that are wound together, a lot like a solar prominence. And here you see linear structures going out, which we believe are what seed the filament growth. See these very thin structures like this right here. That the rising bubble tangles the field, as we heard about yesterday. The tangled field regions also compress and stop conduction so they can cool. Once they're cooling centers, some of these may be able to grow by condensation. There's another factor, though. The filaments also contain dust. So you really want to pull the dust out of the medium from the galaxy, not out of the cooling intercluster medium. So you have this real tricky business that you have to contain some kind of dust to make the molecules in the star formation. Okay, what's going on in the history? If you look at the center of the galaxy, you see all these star-like things. And these were recognized back in the 1990s to be star clusters. And these are massive star clusters, and in a study done by Carlson for his PhD with John Holtzman, part of the WIFPIC-2 team, we saw that the clusters are roughly an age of 100 million years. There's a gap, and then there's redder clusters that are consistent with globulars that are fainter. If these, at this age, these have absolute magnitudes of like -13, so they're 100,000 solar masses and above. So, some time ago in the center, there was really extensive star formation. The presence of 100,000 solar mass clusters tells you you had a high star formation rate region. So that may be part of the secret, that a rapid star formation phase initiates this whole process. As you'll hear in the last 2 minutes as I finish, and Scott stands up next to me, that this is probably part of what's going on, is a multi-level process. What about star formation in the outer region? The clusters were here. Here is the WIN image. You can see this big loop, which was actually detected back in the 1970s by Tom Adams. Large trails of star formation. Star formation is not necessarily associated with just the inner regions, but also with the outer filaments. And this is something that we've been doing with Becky Canning for some time. And here are these loops of star formation, some associated with filaments, some not. Again, to give you an idea, this loop, which we're going to focus on, just think of this as being the rim of Andromeda. You've got the scale about right. Here's the northern structure. Here's one that is associated with a filament. And if you look in the ultraviolet, like this, with the solar blind channel, you see clusters of stars and diffuse star formation, both wavelengths. So this is a very young stellar region. Age is roughly 30 to 100 million years. So these are young stars. And you get an idea of what the mass is. The masses are, again, in the range of order up to maybe a few times 10 to the fifth, 30,000 to 100,000 or 300,000 solar masses. So what you're seeing here is star formation in the outer region of the galaxy that seems to be associated with the disruption of filaments. You get these huge loops that are very coherent, that are filament-like. So this is a second sink for the cool gas. So cool gas, once stored in filaments, doesn't stay there forever. And by the way, this could be a mode for globular cluster formation, where you can make stars out in the middle of nowhere via this kind of lobe interaction magnetic field structure. The picture we have is that the flux tube moves outward, the velocity of expansion slows, the shearing stops, the thing becomes unstable, and I don't know if you noticed, it was beads on a string kind of structure. Okay, if you look at the galaxy in a little more detail, you see lots of substructure in it. This is now with a smooth background. Here's the high velocity system up here. This hole is an artifact, but these features are not. So how much of this is also due to the past history of the galaxy? We're just working on this now. How much is from mergers? How much is from star formation? Of course, mergers are an important factor in central cluster galaxies. We're doing some work with a group at Urbana, Group Mani, who is a graduate student, and Paul Rickard, just looking at, for example, a merging group, and you get these kinds of structures. and that such mergers happen in brightest cluster galaxies. Was very nicely in the astronomy picture of the day yesterday. Double nucleus sitting in there with star formation. Why star formation? Merging galaxies are not actually dry, they're a little bit damp, and you get some residual star formation left over. So you have another process to worry about in terms of the cycle of material. How does this all work? You can start with a cooling inflow, make a dusty gas disk near the center from left over from stars, typical of an elliptical. Star formation and turbulence. It's really like the AGN. Get an out filaments of heating, star formation and evaporation, eliminate the cool material and go around in the cycle. It's unlikely that this thing runs continuously based on both statistics and the structure of the galaxy. So here are my conclusions, which is that even though it's only one galaxy, NGC 1275 and other galaxies that are nearby are a fantastic laboratory. They tell you that feedback does go on, but it also tells you right away that it's not a simple one process, 1D kind of thing. Interstellar matter is often multi-phase, and the multi-phase really matters, and it involves both the flow of gas between phases and into and out of stars. Thank you. Joel.
So this has been an object that's been a headache since,
Your headache is my,
first
yeah.
explained it.
I'm sorry, you can have a little coffee, it'll be okay.
There's never been particularly great explanation for all the crazy things going on here, but, you see gas that has dust and it's molecular,
Right.
and it seems like that would be difficult to condense
No,
out of a hot medium, whereas it's the natural thing that you get when you just strip gas from a galaxy. So why isn't that a viable explanation?
First of all, I think if you strip gas from the galaxy, you have to bring it to a rest in the center with the dust intact. So maybe you can do that. But if you look at that infalling galaxy with those molecular clouds and you work out the density, they're either going to disrupt with hard shocks, 3,000 kilometers a second.
Not if they're in streams. They're in streams that kind of protect itself.
Yes, maybe, but they're also star forming and blowing up, so they're not the simple models.
It seems like it's a lot easier than forming dust and molecular gas in situ.
Well, the answer is no, you don't form the dust in situ. Let me repeat what I had in mind. The dusty gas collects in the center of ellipticals generally. Most ellipticals are damp. It's the process that starts moving this dust out of the center, and then the hot gas condenses around these regions. The dusty gas is carried out by the radio bubbles. In the test of this, which I think actually this thing passes, is the dust to gas ratio is not solar, but it's down by a factor of something like 10. Which is enough.
This is actually directly following on. So I had basically the same question, I guess, which is, was your picture that molecular gas forms inside galaxy and gets pushed out by the bubbles, or stuff gets pushed, maybe ionized gas gets pushed out and then molecular gas forms in those filaments?
Both, but you need the dust. I mean, Joel's point is absolutely essential. You need the dust. On the other hand, I didn't show this, didn't have time, but if you look along the filaments and you look in a blue image, you don't see dust absorption. The absorption is weak, yet there's molecular gas present. So we wonder if the dust to gas ratio might be much lower, but that's still fine for star and molecule formation.
So the coupling is basically ram pressure?
The coupling would be accretion onto the filaments.
And what's pushing the molecular gas out?
It's actually the equivalent of ram pressure.
Yeah.
It's the rising bubble plus the connected magnetic fields.
Okay.
You need to do that.
So
Now, is this
magnetic
right?
fields.
And the answer is you certainly see dusty filaments in other systems that indicate this kind of thing is going on. I think the argument, by the way, against an infall is you really have to slow this stuff down. And you have to let it collect again.
There's lots of gas around to decelerate it. Doesn't sound like it's that hard.
1,000 kilometers a second is pretty impressive.
Yeah, I think it's hard to stop it.
Ram pressure.
I mean, the other way to do it, to answer the question, is you could have a recent merger. That's why we're looking at it. A damp merger could do it. Then it comes in more slowly. I agree with you there. But again, it doesn't make filaments.
Andre.
I had a really similar question. You're lifting the dust. Can you
Yes.
also lift the cold gas per se, so that cooling the...
The answer is the mass is too high. You don't find these central things with 10 to the 10th solar masses of molecular gas.
But do you expect to leave some of the core
You expect to
gas?
miss some of it and then to further grow the mass of the filaments is the idea.
That would be good to quench central
To quench it, right, exactly. It's just an idea though, it's not proven quantitatively.
It's a very short, because it's an easy question. Why is it necessary that the AGN feedback seeds the filaments? Why couldn't this be a heavy star burst?
Actually, I made a model with the Brazilian group trying to do it with a starburst. It's energetically hard to do. The difficulty is that for the starburst, you want everything to sit in a disk or some kind of very planar structure. And it's then, even though you produce shells, you don't get you don't get this 3D structure. Also, you don't get the correlation between the filament holes and the bubble holes and the filamentary structure that's seen in this and other galaxies. So I think the two are linked, and the starburst might in fact mess up a disk so that the bubbles in the jet collect with it better, but I don't think the starburst alone does it. A quantitative model has trouble getting there.
Let's thank Jay again.